In this video in our series on integration, we're going to look at integration by parts, and we introduce this by looking first at the product rule for differentiation. So we know that if y is the product of two functions of x, u and v, then the derivative with respect to x of that function is v du by dx plus u dv by dx. Okay, and that's proved elsewhere. Now what we're going to do with this is we're going to create a similar kind of rule for integration, a sort of product rule for integration, and this is how it works. So we start by literally integrating each term. That's why I've left some space there. So I'm just going to integrate each term with respect to x by putting an integral sign in front. And then a dx there, okay, and then I'm going to integrate this term also with respect to x and this term with respect to x. Okay, so term by term integration of the whole thing. Now the next thing I'm going to do is recognize that this first part here, if you integrate the differential of something, you integrate the derivative, you're just going to get what you started with. So this part on the left is now just uv. Okay, so I know that uv is equal to this integral plus this integral. Okay, so it's the integral of v du by dx, okay, with respect to x, plus the integral of u dv by dx with respect to x. Okay, and all I'm going to do now is just put this first term in front and subtract this term from the left hand side. Okay, and I end up with this result here, which I've produced underneath. Okay, so I've just basically rearranged that function, that arrangement here, to give me that one there, and that is essentially the integration by parts formula. All right, so what does it actually mean? Let me just put a box around it. So we've got this formula now, which we can use to integrate a product of two functions of x. Okay, but you'll notice that in order to proceed with it, one of the functions has to be defined as u, and the other function has to be defined as dv by dx. In other words, it's got to be something that's been differentiated, because we have to integrate it to get v, okay, and then later on we're integrating it again in another product. So that's the formula we use, and it comes directly from the product rule. So how does it work in practice? Well, on the next screen we've got some examples of how it works. So I'll move over, and I've copied that formula again so you'll be able to see it. Okay, so there's our formula up in the corner for integration by parts. Okay, so we'll be using that, and we'll be solving these three integrations. So in the first one, we have the product of x times the root of x minus 1. And what I'm going to do is decide which of these parts is going to be called u and which of these parts is going to be dv by dx. Now, u is the one that you're going to later be differentiating, you see. So usually we choose something that's likely to differentiate to a number, and in this case that will be x. So this is how I would set it out. I would start by defining x to be u, so I say u equals x, okay, and therefore du by dx equals 1. Okay, so I collect this initial information before I start. Okay, and then I say let dv by dx okay, dv by dx equal the other part of the product, which is x minus 1 to the half. Okay, I'm going to write it like that. Now you've got to now find what v is by integrating that. Now to integrate that, you have to recognize that this is the chain rule in reverse. It's a recognition problem. So the answer is that v is the integral of dv by dx, and the integral of this is you raise the power by 1, okay, and divide by the new power. So it's going to give you 2/3 of x minus 1 to the power of 3/2. Okay, now I can do that because the differential of x minus 1 is just 1, which would be sitting outside the bracket. So if you considered the differential of this thing here, you would say x minus 1, you would drop the power by 1, so it would become a half, and you'd multiply by 3/2, which would cancel out the 2/3 and get you back to this, you see. So it's relatively easy to spot that. Now, having got those initial bits of information, I can go on with the integration. So I can say that I equals, okay, now it's uv, so u is x, and v is the thing I've just written down here. So I'll put that in a big bracket next to the x. So it's 2/3, okay, of x minus 1 to the power of 3/2. Okay, now I then have to subtract from that, okay, so I'm at this part here, the integral of the same thing I've just written down, okay, so the term for v that I've just written down, I rewrite it again with an integral sign in front of it, okay, to the power of 3/2, and that then has to be multiplied by du by dx, and we said earlier that du by dx is 1, which makes it easier because it's now just a number 1 with respect to x. Now it's important, especially when you start out with this, to set all your working out fully and clearly, okay, because very often people go wrong, especially with this minus sign in front of the second integral. All right, so that's the first step. Now we're going to tidy it up a little bit because we've got to integrate this again. All right, now it's a similar process to what we did up here, okay, but let's just write this part down first. So I is therefore equal to 2x over 3, 2/3 of x, times x minus 1 to the power 3/2, okay, and from that we're going to subtract the integral of this. Now if you consider the integral of x minus 1 to the power of 5, the differential of x minus 1 to the power of 5/2, that will reduce to give us the 3/2, but it will also put 2/5 in front of this. So it's going to be 4/15 of x minus 1 to the power of 5/2. Okay, now you can check that just by differentiating that last part there, and it will return to this here, okay, using the reverse, using the chain rule. Okay, so that is the integral of that expression there. Now you can actually do this by substitution, a different method, and you'll get the answer in a different form. All right, but mathematically they're equivalent. Now I'm going to put here as well a very important thing, which is plus c, a constant of integration, an unknown number, okay, that we don't yet know what it is. And if this was a definite integral with limits, we wouldn't need the constant of integration, we would just evaluate it. but any integration that's indefinite must have a constant at the end. So that's a result for the integral, and you could simplify that a little bit by taking out a common factor of x minus 1 to the 3 over 2, but I'm going to leave it like that for the purpose of this video. Now the next one we're going to look at is this one here. I'll do this in a different colour. This is the integral of sine x cos x. Now again, you could easily do this by substitution or recognition, because you have the differential of something next to itself, okay? But we're going to use parts and show that it can work that way as well. So I'm going to say let u equal sine x, okay, which means that du by dx is cos x, okay, du by dx is cos x, and I'm also going to therefore say that let dv by dx be the other cos x, or the cos x that's already here. So my dv by dx is cos x, which means that my v is actually sine x. Okay, so it's quite easy, this one, because it's very conveniently just using sine and cos. So what I'm going to do now is I'm going to say that the integral of this, okay, is equal to, so I is equal to uv, so it's sine x times sine x, okay, which is sine squared x. I can put that in straight away like that, okay, minus the integral of v, which is sine x times du by dx, which is cos x with respect to x. Now you might be thinking, well, that looks simple enough, except there's an obvious problem, because the very thing I'm trying to discover, which is the integral of sine x cos x, has just reappeared in the question. But that actually is going to make this work very easily, because what I now do, and this is the wonderful thing about this method, and it often comes out this way, that implies that I, which is the integral of this function here, is equal to sine squared x minus I. So if you now add I to both sides, you get that 2 lots of I, in other words 2 lots of what you're looking for, is equal to sine squared x. Okay, and therefore I, the integral you want, is simply half sine squared x. Okay, so I equals sine squared x over 2, or a half sine squared x. Okay, plus c. All right, so really I'm going to just take that down here, because you can't leave that c out. So let's put it down here. So I equals a half sine squared x plus our constant of integration. All right, now that's a result. There are other ways of getting that. In fact, it's very quick to do using the substitution method as well. But I'm going to highlight that as the answer for the moment. That's the answer to that first one there. And we could have done the parts the other way, where we used the u as cos x and the dv by dx as sine x. And the answer would have been then negative a half cos squared x plus c. Now that would have been a different c in that case, but that's fine, because if it's an indefinite integral, you leave it as plus c. If it's a definite integral, the c would cancel out anyway. Okay, so we'll talk more about that in another video, but that's an answer for the integral of that. And if you do differentiate that, you will get back to sine x cos x. And here's a really interesting one, because when you look at this, you think I equals the integral of log x, but what are the parts? There's only one part, which is log x. We know the differential of log x is 1 over x. So how do we integrate this? Well, we do a little trick. We put in front of the log x, we create a part, and the part that we create is simply the number 1. So we put a 1 in there, so it's 1 times the log of x dx. And then we do this. We say let u equal log x, because that's the one we're going to differentiate. Okay, so if u is log x, then du by dx is just going to be 1 over x. Okay, that's the first thing that we do. And the next thing we do is we say that the dv by dx, okay, is equal to the 1. All right, that's the other part. So this is the 1 is the dv by dx, and the u is the log x. Okay, so dv by dx is 1, which implies that v is actually x. So it's kind of the opposite of what we were doing earlier when I was talking about getting the one that's sort of closest to a number being a number. But in this case, we have to go the other way around, and you'll see how this works now. So using my substitution here, the integral of u dv by dx, so I is equal to uv, so let me do it down here. So I is equal to uv, which is x, v is x, and u is log x, so it's x log x, okay, minus the integral of v, which is x, times du by dx, and du by dx is just simply 1 over x, okay, with respect to x. Now, x times 1 over x, of course, is just 1, and the integral of 1 is x, so that's equal to x log x, x times the log of x, minus the integral of 1, okay, which is equal to x log x minus x. X log x minus x plus our constant of integration c. And that is it. That is the integral of log x. Okay, a very interesting result done by parts when we only actually had one part to start with. Now, this tool of integrating by parts, along with the other methods of integration, opens up a whole world of solutions to things that you previously wouldn't have been able to integrate. So this is just an introduction. There will be a lot more examples to follow in later videos, but I hope this was helpful, and it may be worth you trying to integrate these two by substitution method and comparing your results. Okay, take care.